So we had a pretty simple model of an electron on a wire, and we modeled it as a particle. Now there were some good things about that model. It was easy to calculate the energy of the electron as the kinetic energy. And there were some bad things about it. It was giving us continuous energies, which would imply continuous spectra. And we know that the energy states of an electron, when it's trapped in a small space like a wire or an atom, are quantized, can only take on certain values. So there were some ways that that model was unrealistic. Let's see if we can get a better model by modeling the electron as a wave on the wire. Now here I've got a guitar string stretched between two blocks, and I can put a wave on it by plucking it. So if I grab the wire and I pull it up and then let it go, it will twang up and down like this, and that'll make a wave on the wire. Now I want you to notice right away that I am not free to put any wavelength of wave on this wire. It's got to only be certain ones. If I look at the end points here, where the wire is kind of joined on to the block, I can see that the amplitude there has got to be 0. So I have a restriction. Amplitude's got to be 0 at the endpoints. Now, places where the wave has got to have 0 amplitude are called nodes, N-O-D-E-S. So that's going to be important later. Now, there are other ways for me to make waves besides just plucking the guitar string in the middle. Here are some other waves that I can make. For the second one down here, I could put my finger right there and create a node. I'm creating a point where the amplitude's got to be 0. Now, I'm going to have to, when I pluck the string, it's going to move up and down on either side of that node. So it's going to seesaw up and down on either side without moving at that one point. Now, this time, I've got a peak and a trough, or I've got a trough and a peak, depending on how you want to look at it and when you look at it. But there's still an integer number of peaks and troughs along the length of the wire. Now, look at this bottom one. I can put my finger here and create nodes there. So there's 0 amplitude at those points. And then I pluck the wire, and it will go up and down on each one of these thirds of the wire. And again, I have 2 peaks and a trough, or if I look at it an instant later, I would have 2 troughs and a peak. But I have an integer number of peaks and troughs along the length of the wire. That integer number is important. Let's call the number of peaks and troughs that you're allowed to have along the wire n. Now, that's an important number. It's called a quantum number. And it's going to determine that we're going to have eventually discrete energy states, just as we know we do actually get with electrons and atoms. So for this top one, n is equal to 1. The quantum number is 1. For the next one, n is 2. It's the number of peaks and troughs along the length of the wire. And n is 3 for the third one here. Now, that statement I keep making, there's an integer number of peaks and troughs along the length of the wire, is going to help me figure out what the wavelength of this is allowed to be. I'm going to take that statement and translate it into math. There's an integer number, that's the n, of peaks and troughs. Each peak and trough is a half of a wavelength, so I can put wavelength divided by 2 in there. And if I multiply the number of peaks and troughs by the length of a peak and trough, I have to get the length of the wire. So this equation that I've got here on the bottom is a restriction on the wavelength. I could turn it around and solve it for wavelength, and it would tell me what the wavelength was. Here, the wave on the top one here, the wavelength here is half of a full wavelength. So the wavelength for the top one, when n equals 1, is L over 2. What's the wavelength for this one, for the second one? The second one is going to have a wavelength that is, there's a peak and a trough. That's a full wavelength. It's a full cycle. So you can say the wavelength is the length of the wire in that case. And for this third one here, you've got a wavelength is a peak and a trough. So that's one wavelength. And then you have another one. So you have 1.5 wavelengths along the length of the wire. So a wavelength is 2/3 the length of the wire in this third one. All right. What's important is that we have this restriction. And this is where two important things are happening here. One is we're getting a quantum number which labels the different states that we have for the wave on the wire. And the second thing is, because the wavelengths are quantized, only certain ones are allowed, the energies are going to be quantized. And this is showing you how quantization actually happens.